Thank you. I'm happy to be here this morning. My name is Dave Plonka. I'm with the University of Wisconsin at the Madison campus, and I have an incident to tell you about, and it's still in process of being of us engineering a solution to this. So the reason I wanted to be in this venue is to vet this proposed solution with you folks. So what I'd like to talk to you about is, I'll first give you an overview of what this incident was, and I put the URL here where there's a detailed technical write-up of the incident initially and where it's gone since then. We'll talk about the engineering flaws having to do with the products and also the entire engineering process in terms of internet engineering, not just this product. And I think I'm not going to dwell on that in this presentation, but I'd like you to think big picture about what this means for all of us building an internet. We'll talk about the current status of our particular situation, possible end games, and then I'm going to propose this operational strategy that we're going to take. And I'd like your feedback, either here or in the mailing list afterwards, on if you think this is the right way for us to go, because you're players in this too. Before I start this, though, I'm interested to see a show of hands of how many people out there have read about this or know what this is about. Okay, so that's something like 30%. So I'm glad I'm here because I want the rest of you to know what this is about too. So from an operator's point of view, this is what this incident looked like to me back on May 14th of this year. I saw, this is a time series graph, like from FlowScan or MRTG. The current time is on the right, and this is 48 hours of data. This ramp up in traffic it's marked WISCnet. WISCnet is our internet service provider for our campus, and I'm seeing the traffic ramp up. Instead of the normal peak of 40,000 packets per second across our border, I see it ramp up over a couple of hours from 20,000 packets a second up to about 90,000 packets a second. To me, this looked like a denial of service attack. The only thing that was unusual about it, and I didn't dwell on that at the time, is that it wasn't a step function. It just didn't go straight up. It built at what it turns out to be an unusual rate for a denial of service attack. These red bars are showing basically how we responded operationally to it. We ended up just blocking it. We identified the traffic as being UDP traffic destined for an NTP server in our computer sciences department called ntp1.cs.wis.edu, a popular long-standing public NTP server. And the traffic was all coming from one UDP source port, 23457. That number didn't mean anything to me at the time, but after a while I realized it's the number just after 23456, kind of rolls off the fingers, seems handcrafted. Made it look like a DOS because all the traffic was coming from that source port. So, and then the last bit is this is at least tens of thousands of source addresses. So I looked at the flow records, saw source addresses all over the place, said forged sources. No problem, I'll block it as usual, go away in a couple hours, I'll take the block out. So what you need, this traffic was all destined for our NTP server. It was using a protocol that I didn't know before I did this deconstruction of what happened here, but there's a variant of NTP called SNTP, or the Simple Network Time Protocol. Like all other protocols with simple in their name, it's not necessarily simple to implement correctly, and I think you'll see that here. So beware of SNMP, SMTP, and now this protocol as well. The expectation, though, is that this is used most commonly, for instance, by Windows clients. You just ask, like a DNS request, you send one packet out asking for the time. Almost none of the NTP fields are used, just saying that you send the packet, that's the request. You get an answer back, and it has a time in one of the fields, and you populate your clock on your system with that. It's defined by an informational RFC, RFC 2030, circa 1996. NTP is specified, it basically piggybacks on NTP, which is specified by RFC 1305, which is a draft standard. I think it's interesting that it's an informational RFC and that the others only achieve draft standard state at this point. I think that has to do with the ICAP is a different thing now than it was back when this work was done. So anyway, the protocol is designed so that the SNTP clients, though, all these millions of clients all over the world can just utilize the existing wonderful public NTP infrastructure or any NTP infrastructure. So let's go back to our story from an operational point of view. 1 month after I put that block in, I was looking over all of my measurement statistics, and I found the most active measurement that we had was this blocking of traffic. This was more active than any interface we had in the statewide network WISCnet. And so I did a time series graph here over a number of days showing we're getting like 250,000 packets a second that were dropping at the border of WISCnet here. And the red line here where you see that traffic drop off, that's where we requested one of our upstream service providers, Genuity, at the time, to block it upstream from us. And you can see that only had a little bit of an effect. We knocked 100,000 packets a second out. The other thing that's interesting about this is from left to right, it's growing slightly. So it keeps going up. That's subtle and hard to see from your point of view. So the part I just skipped here The part I just skipped here, and you could see in the technical reviews, how we basically reverse engineered what was happening here, did a bunch of security-based operational work, contacted other sites to find out what was going on. But what we traced it back to was these are the sources of this traffic. There's at least 4 models of this Netgear product. And I talked about this bigger engineering thing. Think about this not just about Netgear. This is any product like this, or all these homogeneous kinds of internet hosts that we're getting out there now. These are small, practically disposable devices, and they're being deployed like crazy. So here's the models. If you use these things, there's new firmware out there. We've gotten a ways along in the proposed solution to this that's out there. But they're boxes like broadband devices. They're deployed places where and DSL, large DSL installations in Europe, in Australia, in the Far East. They're in the U.S. of course as well. So those are the pieces of equipment that are responsible as sources of the traffic. So what happened here? This is my interpretation of what are the engineering flaws here. So what happened is they put an SNTP client in these boxes to fetch the time. The box doesn't have a battery-backed clock. That's one of the reasons why it's very imperative that they get a time, because otherwise none of their logs have any timestamps, and some of the features of the product don't work because it can schedule policies. The SNTP implementation has a hard-coded IP address in the firmware. This IP address, this is the IP address of our NTP server. It's right in the firmware. It's shown in no user interface. The user can't change it in any way, shape, or form, and it's put in there on the production line. There's over 700,000 pieces of equipment today that have this in their firmware. That's another thing is, in hindsight, I realized that this had been going on for a year or more than a year. These devices were in there, and we just didn't know. And they get deployed, and because our time server worked, everything was happy. So my interpretation, then, I tried to annotate this with what I think is wrong here. It violates, in my estimation, the Internet Registry IP allocation guidelines, which suggest that IP addresses are leases. So one of the things I want to remind everyone is that IP addresses are leases. They're not going to be there permanently. It's something that happens to be that way in today's Internet, but might not be there tomorrow. The other thing is these products are really Internet products rather than network products. Those of us that have a number of years' experience with gear, we think of them as network products. You're going to deploy them on a private network. They work on a test bench, or they work on the big I internet. It's not, you can plug them in those different places. These products are targeted for people that want to be on the internet, and so they can utilize services that are only on the internet. That's probably something that's wrong, I think, but these products are out there and they're sold that way. The green portion here is what we've done so far, meaning the vendor, the university, or the review team that we put together to tackle this problem. So code changes were released from July through September that no longer hard code the IP, but now they hard code the domain netgear.com. I don't think that's a panacea either, but that's a much better situation for us anyway, because you can remotely influence their behavior now by changing the IP address to which the names point. And then lastly, the blue is showing what I think needs to happen in the future and some of what we want you to comment on afterwards. So we need to dedicate a portion of our network to service and implement an operational strategy for this, because these things are intrinsically tied to one particular address in one of our legacy Class B networks. And we'll go into a couple details of what's going on there. Another engineering flaw is that the SNTP implementation violated the NTP rules of engagement, or netiquette, for using public servers. They never notified us that they were interested in doing this. The specification for SNTP doesn't even address how you get together, or how you rendezvous with people that might provide you with the service. That's changed. We worked with Dave Mills and some other people on the review team and got a revision out, which you guys can review now. This draft is out now, updating this SNTP protocol, and it has a best current practices section, an operational strategy section, suggesting how you would go about actually making the people networking happen. The blue part here is what should the NTP community be doing about this? One suggestion I have for them is to deprecate the advertisement of IP addresses in their public indexes. That's just one of my ideas. Another part of the engineering flaw is that the SNTP implementation, getting back to the flood now, polls at 1 second intervals until it receives a response. This was going on for more than a year and we never noticed it. So if you just test this once, this seems to work. So, but in terms of a congestion collapse situation, this is exactly the opposite of what you want it to do. When our service is not there, it's more persistent. And one of the things in the process of going through this painful exchange, trying to get in contact with the vendor, the irony was not lost on me that the devices were being more persistent when they didn't get an answer, and I was being more persistent with their support organization when I didn't get an answer. So what we've done so far is, there's again, the code changes were released that use a less aggressive but ad hoc retry algorithm. Just people pulled up numbers. Well, maybe we should wait a bunch of hours instead. Maybe we should only retry a certain number of times. So that's what the current code does, and that's what's shipping today. The other thing we did is, again, updated the simple network time protocol specification to specify other behaviors than this, basically saying don't ask more often. That was implied in the NTP specifications before, but unless you poured over it, you wouldn't, and you were an NTP guru, it might not have been obvious. And the question is, will Netgear code changes in the future comply with this? And the reason that's a big question is because organizations like this, they use other people to design and manufacture their equipment. They use what's called an ODM. This was something that was new to me, an original design manufacturer. And so if you get a company like, it could be anything, Belkin, Netgear, or whatever, they're sort of a facade. They're responsible for getting the name out there, getting the space on the store shelves, but the stuff's shipped out to, in this case it was Taiwan, was where the designer was, and the stuff was manufactured in China. So I could actually reverse engineer what the product does faster than they could get answers from the developer to find out what it was intended to do in the first place. And that's just something that's going on the internet right now. So it's not about this specific vendor. It's something that's going on, and you need to be aware of it because these aren't the handcrafted TCPs that we were used to working with years ago. These are quick turnaround, 3 to 4 month development cycles, that kind of thing. Another part of the engineering flaw, and this is getting to the less tangible part, the designers and users are generally unaware of the problem. So when this time thing stops working, what I found is no one cares about this. These people that bought these $20 or $40 boxes don't care that it knows the time. So the flood keeps happening in all these from these 700,000 sources all over the world, but no one knows about it. So my solution, we'll see if it's a solution, is to go on this outreach campaign to talk to small subsets of users, network operators, administrators, the people that I think are players in making sure that this doesn't happen again. Because that's the whole goal here, right? Internet engineering, the whole goal behind it all is to obviate failure. That's engineering in general is about that, whether it's civil engineering or whatever. So let's see if we can get the word out so that this doesn't happen again. And if you think it's a one-off thing, it's happened before. That's the other thing, is I didn't know about this, but this happened last year with SMC gear in a time server in Australia. And they didn't have as good a success with the negotiations afterwards, such that the vendor stopped talking to them after they produced a code change. We have an extended relationship now with this vendor, and I think we're building a good solution here. But that's not always going to happen, so it's really imperative that this doesn't happen again. I said I'm producing a draft. I have produced this draft. I sent it in yesterday, so it'll be available soon. That I called embedding IP addresses considered harmful. So just talking about the one aspect of embedding the IP addresses in a fixed configuration in firmware, we want to make sure that we've all thought about that, and is there ever any instance where that should be allowed, if they're not, for instance, RFC 1918 addresses. So another question is sort of as a follow-up, and I don't expect to get this in this venue, but how do I reach other participants in this? How do I reach the designers? I don't know. Should I be going to Interop or something? Where do these designers go? I'm not going to fly over to Taiwan and knock on doors or something, but I want to reach that community, and then the manufacturers and the vendors that are getting these things built, because they need to know this is going on. There's also certification labs that some of these companies hire to get basically approve it for being an enterprise class firewall or something like that. These devices don't fall in that category because they're meant for residential use, but theoretically it seems to me certification labs could be offering another service, basically saying that this appears to comply with RFC whatever, it appears to comply with an IEEE standard. These are not the things that get printed on the boxes when you go on the store shelves. The user doesn't care about that, but the manufacturer should, so that they don't have to have one of these awful conversations with people like me. I mean, if you do this, if some accident like this happens again, I guess everyone else would wish probably that the destination of the traffic wasn't all a place where we had more internet traffic measurement than you can imagine. I mean, I had all they were completely instrumented, and now I've got all the postmortem information I need. But how do we get this? How do we get this to change so that people pay attention to what the RFCs are? Because we're really self-policing right now. And if you talk to somebody outside the field, they say, well, what's like your underwriters' laboratories that make sure that all this happens? We don't have that sort of a thing. The last of the engineering flaws is that the communication channel to their engineering was ineffectual. And again, I think this is an engineering problem because in internet engineering, it's all of us as participants. It's not just it's the manufacturers, the users, the administrators, the operators. We all have to be able to communicate to produce as the end goal we want. And when a failure happens, that communication channel has to be utilized to disseminate the information about the failure. Because if you don't know the failure happened, if we just do a deal with Netgear and it gets covered up, no one knows it happened, and it's almost certain going to happen again. So in these kind of things, when we're deploying all these hosts, there's a mismatch I'm proposing between the deployed host impact and those organizations' support or ability to support the users when a problem occurs. So that's something that's new that's happening in the internet, a lot of these low-cost hosts, and you just can't get in contact with the people responsible for deploying them. The current status of this. Right now, we're doing our best to continue to service the requests. We put a couple of rate limits in upstream, we watch the stuff, whatever, so we're servicing the requests right now. So the good news is, from a customer's perspective, you're still getting the time from us, we're running a good time service. We still get occasional spikes in traffic, and this has to do with if the end-to-end path between any large population of these hosts and the server is cut, then what happens is they start slowly progressing into this 1 second retry mode, and we get this build up in traffic like this. It's not something I like to see when I come in the morning. The other thing about the current status is, in terms of the scope of this, there's over 2,400 autonomous systems where these sources are located. So I'm probably not going to ask all you folks to temporarily block these things. In fact, I don't want you to do that. We think we have a good solution to this. To give you an example, for instance, 1AS, Deutsche Telekom, has 76,000 of these things. This information is a little skewed because other providers use multiple AS numbers, but that's sort of what it looks like. So the largest AS has only 13% of these, so if there's no one place I can just go, oh, please stop it right there, and then we'll be okay. This is the number of clients that we observe at our location over time. So on the left is June, and on the right is current. I just did this graph yesterday. We've grown from 500,000 clients we're seeing query that have this particular characteristic to 700,000 on the right-hand side. So we're approaching what we know their manufacturing count, or what the manufacturer reported that they produced, 720-some thousand at the time. I think these spikes are either DHCP effect things, or there are other clients that are out there that I don't know about yet that are also using this same source port. So I can actually track the deployment schedule here. We knew that they were manufacturing these things at like 11,000 a week, and that's about the rate we see here. It also shows what was in the supply conduit out to the users. So at the left side of this graph, this was already, we knew what was going on here, and we were already stopping to push more of these things into the supply channel, but this stuff was all out there. So there's a pretty big lag between the time you make a change and the time it's actually going to get out on the internet. This is also the time that the code change has been out all the time. I mean, no one's upgrading to this new version of the code. And we're just saying we're not going to be able to get in contact with them. They're never going to change. So let's get to the operational strategy, the part that I want to vet with you folks and see what you think. So should we serve these time requests, or should we sever our relationship with them? Well, the behavior is not easily reconfigurable. In fact, it's impossible to reconfigure with the code that's there. Both of us, UW-Madison and Netgear, believe that it's not viable to try to contact the customers. They don't have any way to contact them. People wouldn't, who's going to want, you're going to have to pry it out of their cold dead hands, right? I got this for free. I'm going to use this forever. The other part, so we've developed a multi-phase plan to address this, and it ends in two possible end games. One is an Anycast time service, and the other is to try to suppress the request using the global BGP. So here's our Anycast time service proposal. The cloud in the middle is WISNet, our statewide network, AS2381. It has about 500 sites, 50 peers, 6 commodity internet connections to 4 providers. We have 3 ingress-egress points, so Clare, Milwaukee, and Madison, border routers. What we're proposing is the time requests come in from those different directions, Minneapolis and beyond, and Chicago and beyond. They come in towards us. We redirect them to the nearest Anycast time server. Kevin Miller did a really nice presentation about Anycast deployments on Sunday. I was there, so I know what I'm doing with that, I guess now. The requests come in, the responses go back from the nearest time service, and our idea is to just never let these things get into their failure mode. I can't control the entire end-to-end path, but I can make sure we always have a server that answers them this way. The other possibility is to try to suppress the request using the global BGP. Here I show the cloud in the center is the internet's core. UW-Madison is up on the upper right. We advertise our BGP routes, sans something like a /24/20 out of our existing Class B. Very disruptive to our network, by the way, to be able to do this. But we propagate those routes out with the intent of when the requests come, ICMP unreachables get delivered by the first hop or the nearest to the source BGP speaking router. So we think this is a viable strategy in case of an emergency, basically. So we're prepping to do those things. This network's been used for a number of years on our 128.105 network, and I showed the /20 slice, which is the one that I hypothesized might be a good size for us to split out in terms of BGP. What I'm really concerned about, though, if I try to advertise everything around that /20, what's going to happen with the /20 that I created right next to it? Is it safe for me to put servers and other hosts in that network? Can I expect the whole internet to see that prefix if I do that? So that's one of the reasons where we're leaning towards the Anycast deployment and servicing them, because it's a little less disruptive that way. But I want to know what you guys think about this. Again, we can follow up in the mailing list too. So what I have to ask of you, support the DHCP NTP servers option. DHCPD from ISC has the ability to answer back with an NTP server. If this was ubiquitously deployed throughout the internet, presumably something like they wouldn't have tried to lay this all on a central service. I'm not saying it's your fault or anything, or anybody's fault at this point. It's just that this would really enable what we want to have happen, which is you decentralize it and you get all the stuff out near the periphery where it can be handled by local admins. Please consider this proposed strategy then about deploying an Anycast time service and keeping it as our other card to play the withdrawal of a /20 route or something like that to get the traffic from coming to us. By the way, it turns out to be about 400 and some megabits per second. These are 76 byte packets. If you do the math with 750,000 sources, it comes out to be about 450 megabits per second. So this is a lot of traffic and costs a lot of money to transit to us. Is this the best strategy? Is it safe for us to build this in the internet? Are you okay with UW-Madison using our upstream providers in this way to have this service, basically to service these legacy things that might be gone in 5 to 10 years? Does the WISNet Anycast service that we're providing have enough topological diversity in the internet? Some of you have done these things before, tried to mitigate the stuff like the AS112 project. Does it feel like the right size of solution? That's it. I have, again, the URL for the technical report if you want to see that part that I skipped over about how we reverse engineered what was going on. And then just, again, reiterating an invitation to tell me what you think about this. Does this seem like the right way to go? Because I've told the vendor I want to vet this in front of this community because I think it's important before I start working on the solution. Thanks.
So I think the Anycast, if you want to provide service to these toasters, is a good solution. If you don't want to provide service to the toasters, an alternate solution might be to try and get providers to agree to null route that /32, resulting in the desired ICMP unreachable behavior.
One of my concerns with that is it's sort of, and an operator told me this, it's tantamount to them hijacking our address because we want to maintain end-to-end connectivity if we want to remission that address at some point. So I understand that we could get the cooperation, but it's a lot of people to have an agreement with about trying to mitigate a problem. Thanks.
I have a question. Is Netgear paying for this 400 megs?
Well, so I'm focusing on the technical portion. We're very near coming to, I think, a really good agreement. To characterize it to you, there's two facets to the agreement. They're willing to pay for damage they've done. They're willing to pay for deployment of gear to build this out, or the gear time, the whole thing. And the other facet of it is they're willing to support our organization on its network initiatives. So we're talking six-figure amounts of money if it comes to be. I mean, part of it is vet this, get the line items down, and propose it back to them. But I think that's what's going to happen.
Nice of them to step up to the plate. All right,
Yeah.
so
Well, we asked them to step up to the plate, by the way.
nice of them to at least say they will agree. So.
Mm-hmm.
I don't think you need to worry if you take /20s and vet that out. The internet will listen to your /20s, but it would be nice if you could continue to give service to these people for various reasons. It just seems like
I missed the last part. Was
I said you could take the /20 out, and I don't think you need to worry about the adjacent /20. The internet will listen to you; it'll be fine. But I think emotionally, anyway, it seems like it would be a nicer thing to do if you could continue to provide service for them, especially if Netgear is going to pay for it. The only other thing I could think of is if you ask people to put up Anycast servers, because people can put a time server in their network and route a /32, but then you end up with the same problem. Later on, if you want to use that /32 for something else, it may be hard to extract. On the flip side, if you have a /16, sacrificing a /32 is, honestly, I mean, I would consider it irrelevant. So you might want to contact, like, if you see 13% of them in Deutsche Telekom, maybe have Deutsche Telekom put a second IP on their existing NTP server and statically route a /32 to it. So.
okay. And okay, I want to make it clear that first off, we're not authorizing anyone to do that, no matter how much you want to help, but thanks, we'll consider that. And if we get really big populations of them, we might consider deploying near them.
Thank you, Dave.